Okay, class, we are ready for our third topic in chapter 3 of journal 3. So we did local extrema, global extrema, and now we're doing optimization. And optimization, like many things, is an extension of things you've already learned. This would be those word problems that you saw back in Calculus 1. And so something like this, you often had a word problem, and there's the last several pages of chapter 3 of your journal show a few that you've probably seen. There's one like this where you need to build a shed, and there's some restriction on the amount of the volume. You want the volume to be 256 units cubed, and then you have a goal. In this case, we want to minimize the surface area of this box. And what made it fit in Calc 1 was that they said that there was a square base, right? So then those problems were called constrained optimization problems of two variables. And this was the first time in Calc 1 where you actually had a little bit of a glimpse into R3, because you defined this function that had two variables and it had a constraint. So it seemed kind of complicated, but yet you were able to handle that by pushing the constraint into the objective and forcing this to be a problem of just an unconstrained problem of just one variable. And so what you would do is the method there was you would take your constraint and solve for either variable. In this case, I think it's going to be easier to solve for y. It doesn't matter which one, you'll ultimately get to the same place at the end. And then you would take that constraint, and wherever you saw y in the objective function, this was your objective function, and this was your constraint equation, you would take that and shove it right there. So then what you would get is another problem, minimize f of x, where x squared plus 4x, and instead of y, you wrote its alternative representation as 256 divided by x squared. And now you can look at this and say, okay, that's a function of one variable, and now it's much more comfortable. It was an unconstrained optimization of one variable. So you took something that was more complicated, put it into a form that you could handle, and then you could take it from there. This was first derivative test or second derivative test to get the extrema. Okay, so we're going to do something very similar now that we're in Calculus 3. Our optimizations, same thing. You're going to have a goal, something you want to maximize or minimize. Almost always they'll actually use that wording in the problem, or optimize. You see those are keywords you're looking for. So in this case, I always would tell my Calculus 1 students to write down in words what you're trying to do. So the objective function is we're trying to maximize the volume of the box. Subject to, there's usually additional information. If they didn't give you something else, then you say, oh, make it infinity by infinity by infinity, make it as big as possible. Or if they're asking you to minimize costs, you'd say, make it 0 by 0 by 0, do nothing. Don't go to Lowe's, don't get any supplies, don't spend any money. In this case, maximizing the volume, and then there's additional information which gives us our constraint equation. And in this case, the constraint equation is that we have 12 meters squared. That's a little hint that it's going to have something to do with area. And so we're going to build this thing up from cardboard, and we're going to be doing a surface area then. So we want the surface area of this open box, and that's a key thing, no lid, to be equal to 12, like that. Back over here again, almost always good advice was to start by drawing a picture if the problem was geometric. Some of the ones over here were also like find two numbers, x and y, such that their sum is 16 and their product is maximal. So those were the kind of problems you had. And you'll see some more of those here too. It's often more interesting to work on the physical problems that seem to have applications. Okay, what was my point? Oh yes, so most problems though you can start with a picture. And so we'll do that here. Suppose this is the picture we decided to draw. We want to draw a box. Well, that looks square, but it should be, maybe I'll make it a little more obvious. It's rectangular. Let's just label the sides here. So I'm going to make another copy of that box. Connect them. And let's label this Z, Y, X. It doesn't matter how you decide to label them, how you decide to draw your box. You'll ultimately get to the same place. Your X might have been my Y. That's okay. Okay. Once you've done that, you have your objective function constraint equation in your picture. The next thing is to start, once you've drawn that picture, translating that into words, to get that 12 away from it so it looks a little bit cleaner, right? Translating, taking this picture and combining it with your verbal expression of the problem. And so now we're going to say we have a function of x, y, and z, actually, right? We want to maximize the volume of the box. That's x times y times z. No problem. That's our objective function. Our constraint equation then is translating the surface area equals 12. And we usually say, oh, sorry, I also forgot to say that I want to maximize this function. Maximize f of x, y, z, which is x times y times z, subject to, or such that, the constraint that the surface area is 12. So the open box, it has no lid, so let's say this top part will be the part we'd want to put the lid on, and that would be what, x times y. So we're not going to have that, but we will have the xy on the bottom. So there'll be one xy of surface area, which we want to use with cardboard down here. And then there's this front one right here. That would be z times y, which is also the same as its mirrored one in the back. So we'll have two of those, plus two yz's. And what else? Then we have, do my x, y, y, z. I need xz's. Where are those? Xz's are these. So these sides here, and there's another one mirrored on the back side, so there would be two of those, two xz's. Okay, so objective function, then you're trying to optimize, maximize, or minimize, subject to the additional information, which will always be a constraint equation. And your objective function is always a function. What do you notice about this function? Well, first thing, it's an R4 function, right? Because there's actually like a third variable, maybe we'll call it v for volume, that depends on these dimensions, x, y, and z. So there's three inputs affecting a fourth output, so it's an R4 function. We don't know how to optimize, find local extrema for think about our d-test, right? Our d-test talks about using your f sub x, f sub x, y, those second partials, and it doesn't say anything about handling an R4 function. So we're going to do the same thing we did over here, though. We're going to say, okay, but I'm good. I can't do R4 optimization, but I am good at R3 optimization. I know how to find local or global extrema of an R3 function. So what can I do to make this guy into an R3 function? Same trick. We have this constraint equation, which gives us a way to manipulate, represent any of the variables in terms of the other two. So we're going to pick one of those. Let's pick, doesn't matter, I think they're all going to be equally easy, but let's solve for the z, because we like to usually have our R3 functions with x and y, so let's just stay with that. So let's take this constraint equation and we'll do what's called a solved constraint equation. And we're going to solve for z. So z is equal to, we'll have 12 minus xy divided by, what, 2x plus 2y? Yeah. Right, so these two things are the exact same representation, but I like the second one better because it enables me to get rid of this z, because I can write z in terms of its alternative representation in terms of x's and y's. So that's what we're going to do here. I'm going to take this and force it to go into the objective function. So then I'll be asking, get a new objective, which is an R3. We want to maximize a function of x and y, and it's x times y, and instead of z, it's this fraction, 12 minus xy over 2x plus 2y. And then we're going to take it from there. Where do we find what are good places to look for max or min? In this case, we're hoping they'll be max. Good places to look for those are at CPs, and then do the d-test. So we're going to go through the steps. We'll get to review many of the things we've already done. This will be quite a extensive problem, though. It's going to take us a good bit of time to work through this because I chose a particularly messy one to practice our partial derivatives as well. Thanks from chapter 2. So we'll get to review a good bit. I'm going to need some more whiteboard space. I'm just going to pause this for a second and make a little space. All right, ta-da, clean board. We want to maximize this function here. To do that, we have to find our critical points, which means we need our f sub x and our f sub y, both first partials. So I'm going to clean this up a little bit so that I have just like one numerator, one denominator. So 12xy minus x squared y squared over 2x plus 2y. Okay, so now we get to practice a couple partial differentiation rules. So partial with respect to x, and we'll set it to 0. And then we'll get a partial with respect to y, and we'll set it to 0. And then we'll solve this system of equations and hopefully get a value for x and y. CPs to check with a d-test. Okay, so partial with respect to x. Well, first thing about this that I notice is that in this representation, it's a fraction, I need the quotient rule. So I get to practice doing the quotient rule within partial differentiation. Quotient rule has this structure: denominator times derivative of the numerator minus any more space. Numerator times derivative of the denominator. So denominator, derivative of the numerator minus numerator, derivative of the denominator, all over denominator squared, and we'll set that to 0. Oops. Right. So we can fill in the copy boxes. Those are easy denominators: 2x plus 2y, 2x plus 2y, and numerator 12xy minus x squared y squared. Okay, now what goes in the derivative parts of the boxes I need to take derivatives is the derivative of the numerator, but with respect to x. Right, so now I look at the numerator and I take its derivative with respect to x. So it's a nice polynomial, easier to do the derivative with respect to x, and we'll get 12y minus 2xy squared. And I did the same thing in the last box. It's getting a little cluttered up in there. Maybe I'll get rid of those for a moment, or put them in another color maybe. Okay. Derivative of the denominator with respect to x is 2. Right, that looks pretty messy, right? But the nice thing, let's make some space, is that even though you have a big fraction equal to 0, the only time a fraction can be 0 is when the numerator is 0. So I really just have to focus on this part here in drain, solving that. Again, it still looks kind of messy, but I know I'm going to be able to simplify with some algebra and factoring, right? Just distributing. So I'm going to take that green part and work on that now. Let's see. I don't know that green shows up so well. So I'm going to stick with the blue. I'm working on this numerator. And so I'm going to just FOIL some stuff out, distribute that 2 here. So I'll have, let's see. I should probably factor some stuff out though. I should probably factor this 2 and this 2. So let me do that first. That'll be a 2, take out another 2 here, makes this a 4. And that'll be left with a 6 and 1, invisible 1. And that's all I can do there. Okay, so now I'm going to do the foiling. I'm going to have 4 times, what is that, 6x plus 6y minus, oh wait, it's not a minus, that's just 6, right? That was the derivative of the numerator with respect to x was 12y, so just 6. Yes, okay. All right, so 6x plus 6y squared, let's see, minus an xy cubed, and I'm creating one more here, minus an x squared, y squared, and all that's times 4. So I FOILed this out, kept the 4, I think that's right. And then back here, we need to subtract out 24xy and plus a 2x squared y squared. And we want all that to be equal to 0. So hopefully there's some like terms we can combine. Let's see. And here's an x squared. Here's an x squared, y squared. What else? Do we have another xy? Oh, here's the 6xy, right? 6xy. Okay, there's a 24xy. That's going to go with that one. So I've got something like 24y squared minus 4xy cubed minus 4x squared y squared plus 2x squared y squared equals 0. Right, and those can combine, so 24y squared minus 4x y cubed minus 2x squared y squared equals 0. I could take 2y squared out of it, right? So I have 12 minus 2xy minus x squared equals 0. Yeah. Okay. Lots of algebra, and I got down to the place where I need to solve this equal to 0 and see if there's which values of x and y make this true. Then I'm going to have to do the same thing with f sub y. So we're only partially there. Okay, but let's take a look at this one. Right away, we know y equals 0 is one solution. And then the other one is whatever solves 12 minus 2xy minus x squared equals 0. So we'll have something that we need to combine with the f sub y that we're going to need to make space for. Okay, so let's work on the f sub y, or maybe I'll just put it up here rather than showing it. It's almost analogous steps, but you'll be taking a partial with respect to y, still using the quotient rule. I'll pause the video, put that up there. Okay, so I've wrote what we got from our f sub x equation, that we had y equals 0, easy to get a partial part of a critical point. And then we have this equation here. And if we did the same step to get f sub y, lots of work later, we'll get down to this partial. And again, we only have to focus on the numerator, equal to 0. So from this, we can conclude x equals 0. And this other equation, nonlinear equation, looks a whole lot, has some symmetry to the other one we found. But we can also definitely identify one critical point, which is at 0, 0 for this function. Seems like that's a critical point, but if we enter that into the function, we also see, well, 0, for a couple of reasons, 0, 0 isn't going to be interesting to us, because it's saying, remember, we're making a box, right? 0, 0, that doesn't make sense. You can't make a box with those, at least those two dimensions, regardless of what you're going to choose for z. The other thing that's interesting, when you put 0, 0 into this function, remember about domain and range, that this is going to give us a 0 in the denominator, which makes a discontinuity. So you can't really have that. It's not actually a value in the domain of this particular function. So there'll have to be some other critical points, again, to solve this problem. And we're going to get those by looking at these two equations. The two equations, these two nonlinear equations in red. Just take a look at those for a moment, even though it looks like, okay, well, now I've got to solve this nonlinear system of equations, which you could do. There's techniques for doing that. You could ask a tech tool to help you. But also just take a moment and look at it. Again, you see this symmetry. The only way these two equations are going to have the same solution, both be 0, is if x squared and y squared are equal. The only way x squared and y squared are equal if it's that x and y are equal. So let's see what happens to one of these if we let x equal y. So x equals y takes, we'll go to the first one, 12 minus 2x squared minus x squared equals 0, right? So I'm going to use x equal y, plugging it into the first one, and I'll get 12 minus 3x squared equals 0. So 12 equals 3x squared equals 4. X squared, x is plus or minus 2 then. So we have, but we don't care about minuses, right? Because we're doing something physical. So we're going to use the x equals 2. And if x is 2, we got x equal 2 by using logic and reasoning that the x squared equals y squared, so x was y. So 2, 2 is a critical point. Now, if I had just magically thrown that critical point out of the air, dropped it to you as a gift, and said, is 2, 2 a critical point? How would you check? Again, if I gifted you a critical point, a potential critical point, one thing you could do to check is to check, does it satisfy that both first partials are 0? Does it satisfy this? Go back to your notes from the previous page. Does it check that the 2, 2 plugged into f sub x gives you 0? Does 2, 2, so really you're saying f sub x at 2, 2. You're wondering, does it equal 0? It will. F sub y at 2, 2. You're wondering, it's a question, does it equal 0? Yes, it does. This is a critical point. So a couple ways we verified that 2, 2 is a critical point. Okay, so then last thing for optimization problems, you have to verify the critical point is what you wanted, a max, and then you also have to get all the dimensions. We've only got an x and y. How do you get the z value? Z value comes from your, just like I did over here, your solved constraint. So many boards later, let me see, what was our z? Z was, this is what started the whole thing, 12 minus xy divided by 2 times x plus y. So that would be what? When we plug in our value for a critical point, we would get, that's our x, our y, we would get the corresponding z value as a point is 2 times 2 is 4, 12 minus 4 is 8, divided by 8, so that's 1. That works out nice. So we have that these are what we're thinking are the dimensions for this box that maximize the volume. We're trying to maximize the volume subject to the fact that the surface area had to be 12, right? And so this is the only other candidate we have, right? Because 0, 0 didn't make sense. This is the only other CP that we have. So we're really hoping that it is a max. And we can check that with the d-test. That'd be an excellent thing for you to practice. Pretty nasty. It's going to get into even more, right? Even more quotient rules with your partials. It is going to turn out that this is a max, so this is going to be, this maximizes the volume. And we're going to do this visually, but you could also check, again, using one of your tech tools, but I just want to see what this surface looks like. That was an interesting surface for us. So let's share the screen. And go to CalcPlot3D. And to save time, I've put this pre-entered our original objective function, right? It was 12xy minus x squared y squared divided by 2x 2y. That was the volume that we were trying to maximize. That was this thing here, right? So I'm going to turn it on. And I decided to look at -4 to 4. That includes the optimal value that we're thinking about of 2. I went y from -4 to 4 because that also includes our optimal value. So I just want to see what this surface looks like. And remember, we also noticed that it had a discontinuity at 0, 0, right? We said that critical point is a critical point, but it's a critical point because it's a discontinuity. It's not in the domain. This is a really interesting surface, right? This is cool. So let's look at this, and it's got these two, like this cupped surface to the left, and then on the right side, the green part, it bends down. And let's look maybe from overhead and see if we can see that at x equals 2, y equals 2, that's about here, if that actually was the peak. Yeah, that's here on the peak. And you can also check this by looking at the contour map for this guy. So let's just give it what's preset. Let's see what happens. Taking some time to do that. Yeah, here is one at -2, -2. And then that's the blue side, the left side, that was the min. And then I just think I didn't enter enough values, right? I think, oops, go back to this. Let's enter step size maybe of 0.5. And we should see the upper side fill up. Yeah, there we go. Okay, so now we're seeing that this was at 2, 2, those concentric rings. I probably should have even added more. and they're zooming in, and getting closer to the max at 2 because the z values are getting higher, 2.5, 3, 2.5, all the way up until we get to z. And one last thing then is that what is the actual volume, right? And that is volume equals 2 times 2 times 1 is 4. And that is also what makes sense on your contour map because you're taking 2.5, 3, 3.5, and this dot actually has a z value of 4. And remember, does that make sense? Because I had an x, y, and a z. Remember, our original function before we turned it into an R3 was actually an R4, and we had volume was our 4th variable. So that's really what it's representing here with that point of 4. Okay, stop sharing the screen. Okay, so one last thing I want to talk about, and maybe I should review real quick. So third application in chapter 3, optimization problems. Optimization problems are really just an extension of the optimization problems you learned over here, where the key pieces were an objective function, you're trying to minimize or maximize. It will be a function for us, it'll be a function over here when you originally formulated, it'll be an R4 function rather than an R3. There will be an extra piece of information that will form your constraint equation. Over here for us, our constraint equation will have an x and a y in it, or 2 variables. You will solve for one of those variables, or sorry, an x, a y, and a z. Our constraint equation originally had an x, a y, and a z, which for us it was a plane, right? No, it was a nonlinear surface, a 3-dimensional nonlinear surface, and we solved for z, and then we pushed that into the R4 objective and got an R3 objective. The new objective function lived in R3, and we wanted to maximize or minimize, in this case maximize, and so then you're going to take it from there as if it's a local extremer problem. Ours was particularly tedious because I chose one to practice some partial differentiation. Those are some easier ones at the end of the chapter for you guys to work on. Okay, and always make sure you go back, check that your CPs are actually what you want, extrema, by using the d-test. We checked ours visually because this one's particularly nasty. And then make sure you answer the problem. You give them everything they wanted back. Sometimes you might stop with an x and y, but don't forget there's actually usually another variable you need to make sure you get by using your solved equation. Okay, and then last thing I want to talk about is I teach a class every other fall of odd years. It's called Math 451, 551. It's a combined, like, I've had sophomores, juniors, and seniors in the 451, and then this is our master's level, and they're combined in one class. Anybody that's thinking about our Math 4+1 program, we've had some really good chemistry students that decided to stick around and get a master's in math. If you are sticking around for join a 4+1, the 4+1 in our math program enables you to get your undergrad, your BS, and your MS in 5 years because some things are doubly counted. And this is a class for which that would happen because if you're in the 4+1 program, say NIA, and you wanted to take this class, take it at the 551 level, just a little more work, and you'll get double credit for both the undergrad and the graduate class. Anyway, so what this class is, it's called Optimization and Linear Programming. And this class I love teaching Calc 3, I love teaching Linear Algebra 203, and this class Optimization. This one's actually close to my degree. My PhD is in operations research. And it's like these problems to the nth degree, right, on steroids. So we're minimizing and maximizing functions in Rn, a function of x1, x2, we might go up to 10, but we could go 1,000, and we do. There's computer programs that help us. Subject to, rather than just one constraint, it might be x1 plus x3 minus x5 equals 7. It might be x2 squared plus x7 equals 9. It might be x1 is less than or equal to 7, x3 is greater than or equal to 0. All sorts of equalities and inequalities, set of constraints, one objective function, and we can do many, we really do build on all of these things here. And it's also very geometrical, very visual, so visual, right? We come back to these we started class with these polytopes, and some of you built them at the end of chapter 1, right? We're going to visualize things. Similarly, we'll have the geometry of this is very similar to the geometry of what you're doing in R3, but we'll extend it to like n-dimensional space. So again, one of my favorite classes to teach, so check it out. It'll be fall of odd years. Every other year in the fall of odd years. All right, thanks.